Hello everybody and welcome back. Today I'd just like to do the second FRQ from the 1998 AP Calculus BC exam. We are given a function f of x equals 2x e to the 2x. Our first task, or step A, is to take the limit right here as x approaches negative infinity of f of x and the limit as x approaches infinity. To begin, let's first just do the limit as x approaches negative infinity of 2x e to the 2x. And for this, I actually think it might help if we separate this into two limits. So we can do the limit as x approaches negative infinity of 2x multiplied by the limit as x approaches negative infinity e to the 2x. Now, something that we know is that as x approaches negative infinity for this right here, we're going to get an infinitely large negative number. But as x approaches negative infinity for this, we are going to get 1 divided by an infinitely large number, pretty much, because we are raising it to a negative power. So quite simply, we will have a 0 for the second part of our limit, and we will have an infinitely large number for the other part. So we could just write 0 times the limit as x approaches negative infinity of 2x times 0 equals 0. And that is the first part of this problem. For the next part, we are asked to find the limit as x approaches infinity of f of x. This is more simple, more straightforward. So the limit as x approaches infinity of 2x e to the 2x is infinity or does not exist. Alright, so for part B, we are asked to find the absolute minimum value of f, and we need to justify our answer. So to do this, we first need to analyze the critical points of f, or find them. So to do this, we're going to find f prime of x and set it equal to 0. So f prime of x equals, using the product rule and the chain rule, 2 e to the 2x, where 2 here, the constant 2, is the derivative of 2x, plus 2 e to the 2x times 2x. And we're setting this equal to 0. For the derivative, I can factor out a 2e to the 2x, which I will do. And now we have this expression. And because I'm solving for x, I can really just ignore this right here, because this is an exponential, and an exponential will never equal 0. So I'll just cross that out. And now in solving for x, I'll subtract 1 from both sides, and we get 2x equals negative 1 divided by 2, and we get x equals negative 1/2. So we have a critical point at x equals negative 1/2. And now as I erase all of this, I will rewrite the derivative of f like I did when I was solving for x, because I think that's just easier to look at. That would be 2 e to the 2x times 1 plus 2x. So we have one critical point. Now, provided f prime is negative for all x before that and positive for all x after that, then we know that we have an absolute minimum at x equals negative 1/2. So let's examine the derivative at those points before and after. So I can just make a number line real quick. I have negative 1/2, and let's analyze at negative 1 and 0. So at negative 1, we will simply have 2e to the negative 2, which is still a positive number, multiplied by 1 minus 2, which will be negative. So the slope at that point, or the derivative, is negative. And at 0, we will have 2e to the 0 times 1 plus 0, which will be positive. So the derivative will be positive after negative 1/2. So now we can write our justification. Since f prime of negative 1/2 equals 0, and f prime of x is less than 0 for x is less than negative 1/2, and f prime of x is greater than 0 for x is greater than negative 1/2, f has an absolute minimum at x equals negative 1/2, where f of negative 1/2 is equal to, and now if we just plug this in, we will have 2 times negative 1/2 e to the 2 times negative 1/2. So yeah, that's our answer for part B. For part C, we simply need to write the range of f, and this is really simple. Since we solved for our absolute minimum, which was from the last problem, f of negative 1/2 equals 2 times negative 1/2 e to the negative 1, which, I mean, I'll just simplify that further, I guess. That would just be negative 1 over e. Since that's our minimum, we know that the range of f will be negative 1 over e is less than or equal to f of x, which is less than infinity. Okay, moving on. Part D. Consider the family of functions defined by y equals bx e to the bx, where b is a non-zero constant. Show that the absolute minimum value of bx e to the bx is the same for all non-zero values of b. So essentially, since we know that the absolute minimum of f of x equals 2x e to the 2x is negative 1 over e, we should find that the absolute minimum of y for all values of b where it is non-zero is also negative 1 over e. So first, let's just find y prime, b e to the bx plus b e to the bx times bx. And then once again, factoring out b e to the bx, we get 1 plus bx equals 0. Solving for x, since we can ignore this once again, we will get negative 1 over b equals x. To show that the absolute minimum value of bx e to the bx is the same for all non-zero values of b, what we can do is we can substitute this back in to y. So let's do that. We have y equals b negative 1 over b times e to the b negative 1 over b, which equals negative 1 over e. Therefore, the absolute minimum value of, and I'm just copying the wording here, it often helps to do that, simplifies your thought process, is the same for all non-zero values of b. And that does it for the second FRQ from the 1998 AP Calculus BC exam. If you enjoyed this video, please give it a thumbs up and subscribe. If you did not, please share with somebody else who will enjoy this video. And I hope you have a wonderful day.